So I know that this is a format to use. Did I set that up right of 1/4 lambda?
So,
Because that's not n, is it?
mm-mm.
It's more like
So this, if I'm not mistaken, this is for open tubes.
oh.
Because open tubes and closed tubes behave differently. Because in an open tube, we want our wave to end at a node at both ends. Because since it's open at both ends, it has to end at a node at both ends. So its fundamental frequency, or the biggest wave that could possibly fit in this open tube, would be
Maybe 1 full wave.
1/2 of a wave.
Oh, 1/2. Okay. So an open tube always has. Is that a fundamental frequency of just half or?
Yeah, so here we would say the length of this tube is 1/2 of lambda.
Huh. Okay.
So yeah, what we can end up saying then is for open tubes, we can say the length of the tube is always going to be n over 2 lambda. N being whichever harmonic we're talking about. So the fundamental is the first harmonic, the next one would be the second, third, fourth, fifth.
The middle one.
Yeah, for a closed tube, our equation looks a little bit different. It would be, let's see if we can figure it out. So it would be so that should just be n over 4.
I'm a little confused because they're both the top two of these tubes they're both closed.
Mm-hmm.
Yet they have different lambdas or like wavelengths. Well, why is that?
So this is actually, in a closed tube, there's no such thing as the second harmonic, or the fourth harmonic, or the sixth harmonic. It only goes by odd numbers. So the fundamental, we call it the first harmonic.
Okay.
The next possible standing wave is this wave, and we call that the third harmonic.
Okay.
So depending on which harmonic we're talking about, we can always use this equation, which says L equals n over 4 lambda. So when it was the first harmonic, it was L equals 1 over 4. When it was the third harmonic, it was L equals 3 over 4.
Cool. Thanks.
Does that make sense?
Yeah, that makes a lot more sense.
So yeah, maybe it'd be worth our time just to briefly explain why closed tubes can only have odd numbered harmonics.
Okay.
So I'll make it real quick. So over here, let's draw some open tubes. Okay, so here's 1, 2, 3 tubes. We know that the fundamental in an open tube is always going to look like that. That's the biggest standing wave that can exist because this is the first wave that ends and begins on a node. The next possible wave that can exist looks like this. Because again, it begins and ends on a node. The next possible wave is that, because that's the next combination or the next wavelength that begins and ends on a node within this confined boundary.
So it goes in.
So every time it adds 1/2 of a wavelength, or sometimes you'll hear that being called as one turn. So this is 1 turn, this is 2 turns, this has 3 turns. So this is our first, second, and third harmonic. So we can say here L equals 1/2 of lambda. Here L equals 2/2 lambda, or in other words, 1 lambda, because you can see how that's a full wavelength. Here L equals 3/2 lambda. So if we want this same sized wave to be the fundamental of our closed tube, we would have to make that tube half as large, or half as long. So that's about half as long. So again, we're going to start on a node and end on an antinode. So do you see how that wavelength is the same as that wavelength if we were going to continue both of them to be a full wavelength?
Now we're looking at a closed tube, right?
Yeah.
No, it's just we would just make it half the length.
So this tube would produce the same fundamental frequency as this tube, even though this one's half as large. Because just the dynamics of how open and closed tubes work, that's the way, and that's how instruments work. Like a lot of times we have, a flute or something, and it's got these holes in it. And by covering different combinations of holes, essentially what we're doing is we're changing the length of the tube, and then that's creating different frequencies, which creates different notes in our
Okay,
case.
so if we shorten it but it's closed, it'll have the same frequency of a open tube that's twice as long.
Exactly. So now, keeping the same size open tube, let's see what the next available wave is.
So I guess just the key thing to keep in mind is that when you close it, you only need half the length. Is that pretty much?
So when you close it, you need to understand that it's going to be a node on one side and an antinode on the other side. When it's open, it's a node on both sides.
Okay.
So here, the next possible one is that. And this wave ends up having the same frequency, not as this, but instead, this wave and this wave have the same frequency. So that's why this is our third harmonic instead of our second harmonic. So up here we had our first harmonic, which was identical to this first harmonic. Here we've got a wave which is identical to this wave, so we call this our third harmonic. And what ends up happening is that so if we tried to draw this wave in this tube, it would look like this. So that's this wave in this tube. That doesn't work because it's closed. So it needs to end on an antinode on the closed end. So this wave won't exist in this closed tube.
But if that was open, it would be like that, right?
Yeah, for sure.
Okay.
And it can totally be like that. But it's not, it's closed.
So it has to be.
So the next possible wave for this closed tube ends up being that, which is identical to this wave. So we go from first harmonic, or fundamental, to third, to fifth, to seventh, so we go by twos. Whereas over here with our open tube, we go first harmonic, second harmonic, third harmonic, just right down the line.
Okay. Cool.
Does that make sense?
Yeah, it's starting to click a little bit.